In this video, we'll be covering the concept of optimization revolving around the open box method. In this case, you're going to go ahead and start with find the volume of the largest open box made from a piece of cardboard 24 inches square by cutting 4 equal squares from the corners and turning up the sides. The first thing we're going to have to do with this problem is actually write it out and look at a picture. It's not an easy problem to see immediately, but the idea is we're going to have a cardboard box. It's going to have 24 inches by 24 inches. The next step that we're going to identify is that we're going to be cutting 4 equal squares from the corners. So I'm going to cut something out of here, out of here, out of here, and out of here. Those 4 equal corners will be cut out in such a way so that I can turn these sides up and fold along those solid lines, and you'll notice that this piece will come up, 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 and they'll connect at these edges here, 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 and those pieces will be thrown out. So the question is find the volume of the largest open box made. So again, we need two different equations. We need a restriction equation and we need an optimization equation. Well, those equations have to be relationshiped in terms of this image. So the idea is I don't know how much of a space I want to be able to cut out. So I'm going to go ahead and label this length as x, this length here as x as well. Because in this case, if I label this as x and this as x, you'll notice it has to be equal squares from this corner. And every single one of these corners will actually cut out the exact same length amounts. So our restriction equation actually focuses on the concept that this length here is 24, this length here is 24, and we're going to go ahead and remove a length of x on one side and a length of x on the other side. So there's a couple of different ways we can view this, but the way that I'm going to identify it is that in every single one of these pieces, I'm going to have a length, that's this piece here, that's this distance from here to here, that's the length. We're going to have a height, that's the distance from here to here. Again, when we fold this up, that distance right there is going to be your height. And we need a width, which is going to be this distance right in here. So I'm going to call this length right here our width. So we have length, we have width, and we have height. So our optimization equation actually revolves around, again, the volume of a box, the largest open box made from a piece of cardboard 24 inches squared. In that case, I need length times width times height. I need to be able to take the derivative of this optimization equation. In which case, I know what my length is. My length is going to be this distance right here, which is 24 minus x minus x. So my length is actually 24 minus 2x. My width is this distance right here, which actually ends up being the same as this distance right here. Again, you'll notice the width is going to be 24, this whole distance, minus x minus x. So my width is actually 24 minus 2x as well, where my height is x. Again, that's this distance right here when I have to fold this box up. So that distance there is x. So my volume is now a single equation, all written in terms of x. Now here's the kicker. What was our restriction equation? Again, take a minute and think about that. Our restriction equation actually revolved around this entire image, the fact that this is 24 and we're cutting out x and x. So in some cases, our restriction equation is already built into this problem. There is no multiple variables. All we did was utilize this image to create a restriction on the length, the width, and the height. Okay, so now that I have this equation, what I'm going to do is I'm going to view this as 24 minus 2x, quantity squared, times the variable of x. The reason I'm going to view it this way is because it'll be a lot easier for me to take the derivative of this function than it would be for me to multiply these numbers out. These numbers are going to get relatively large. 24 by 24 is not going to be a pleasant number to multiply. So I'll leave it in this form. And again, anytime I want to do an optimization equation, I need to take the derivative, and I need to take that derivative and set it equal to 0. So right here, I'm going to take the derivative of this thing such that I identify this entire thing squared as f, this thing here as g, and I can follow that little formula for the product rule. So the derivative of f is bring down the 2, leave the interior stuff alone, subtract 1 from the power, and again I have to apply the chain rule. What is the derivative of the interior function? Well, the derivative of 24 is 0. I'm going to carry down the negative, and the derivative of 2x is 2. So again, all three of these pieces is the derivative of f. Again, if you're having difficulty with that, f is 24 minus 2x squared. F prime, I have to apply the chain rule, carry down the 2, leave the interior unchanged, subtract 1 from the power, and then multiply by the derivative of the inside. The inside here is 24 minus 2x. The derivative of 24 is 0. The derivative of minus 2x is a negative 2. So this here is the derivative of f. Okay? After I've taken the derivative of f, I have to multiply that by g unchanged. Plus, the derivative of g is 1, that part is easy, times the first function left unchanged. So now I have the derivative here. I'm going to go ahead and tidy it up a little bit by simplifying and combining like terms. 2 times a negative 2 is a negative 4 times 24 minus 2x times an x. So I'm going to go ahead and move that x over here. Again, this x is multiplied by everything, so I'm going to go ahead and ignore that. Plus 24 minus 2x quantity squared. At this point, you're thinking, well, I don't want to FOIL this out. I didn't want to FOIL it out back here. I still don't want to do that here. So I'm going to do some algebra that might be uncommon, but it works a number of times when we have to do a product rule with something that looks like this. You'll notice in this first term, you'll have a 24 minus x in parentheses. That's a plus sign. And then in this second term, you'll notice again a 24 minus 2x. Yeah, this one's squared, but there's still one of those terms in it. So what I'm going to do is, again, remind you that this is equal to 0. And out of these two terms, I'm going to factor out a 24 minus 2x. Then I'm going to be left with, in this term, just a negative 4x, plus, in this term, after I've pulled out one of those, I'm going to have a 24 minus 2x left over. In which case, this is one of my factors, and this is the other one, which I can very easily identify that that's one factor, and this is then 24 minus 6x. So with both of these identified, I'm going to go ahead and set each piece equal to 0 and solve. Because again, anytime I'm trying to solve an equation, I will always set each piece that is multiplied together such that it's equal to 0. A multiplication of two factors equal to 0. I will set each factor equal to 0 and solve. This will provide me, when I solve, a negative 24 divided by a negative 2, in which case x is equal to 12. Or, over here, I'll subtract the 24, and I'll divide by a negative 6, and I will get x is equal to, looks like, 4. So now I have two different options for x. This is very unique, but it is actually not that uncommon. Because of our equation up here, you'll notice it had 2 powers of x here and a third power of x here. That gives us a cubic. The derivative of a cubic will give us a quadratic, and a quadratic set equal to 0 will give us two different solutions. Now, where does this thing get a little bit hairy? We've done all of the calculus. Everything from this point forward is algebra. So let's go back and read the question one more time. It says, find the volume of the largest open box made from a piece of cardboard 24 inches square by cutting 4 equal squares from the corners and turning up the sides. So when I'm trying to do that, my x is one of the lengths. Again, that's the height. And I have 24 minus 2x as the width and 24 minus 2x as the other length. So down here, I'm going to identify that. My volume should be equal to 24 minus 2x times 24 minus 2x times just x. If I were to plug in 4 for my x values, my volume would actually end up being 24 minus, looks like 8. 24 minus 8 times 24 minus 8 times 4. 24 minus 8 is 16, so I have 16 times 16 times 4. Whatever that number happens to be, that unit of measurement, if we look back at the problem one more time, is inches. Again, inches. So volume is inches cubed. And I'm going to go ahead and leave that number as it is for now. Over here, what happens if I were to plug in 12? Well, in this case, I'd have 24 minus 24. Well, wait a second. If this is the case, if I try and use x equals 12 inches and I plug in 12 to this equation, I get 24 minus 24, 24 minus 24, and 12. Why doesn't this work? Well, if we look back at this image, if I use x as 12, that means I'm cutting the box right here. And really, I'm just going to cut it into 4 equal squares and remove all 4 squares. Because again, If this is 24, half of that is 12. So 12, in the concept of this problem, shouldn't make any mathematical sense at all. And you'll notice the volume is optimized. It is the smallest possible volume you can find. But we don't want the smallest possible volume. We want the largest possible volume, which is 16 times 16 times 4 inches cubed.